I mean, okay, great.
Okay. Yeah. I'm taking a look at it, I'll just do it now, give that it's on the big comment. But if I do anything big, at this point, I'll just leave the comment.
Okay, yeah, I guess we can begin. Hopefully everyone on Zoom, can you guys see my screen?
Yep.
Okay, looks good. Cool, cool, cool. Great. All right, so I guess this is a very well-attended vision miscellaneous group talk on DeepSeek and how state-of-the-art language or reasoning models work. So I guess before we talk about what the talk is about, like, we're all CMU students, so we know a lot about AI, but clearly these things have hit the mainstream. So like NVIDIA lost $600 billion of stock market value. Like Apple, Meta, all the stocks were down like in the last week. It was like a sea of red. There's people on Twitter memeing about it. So I saw this tweet. I said, OpenAI, give me 2 weeks and 5 million and I'll clone it ASAP. And then both Trump and Sam Altman have talked about DeepSeek in different remarks. So basically, that to be said, this model's caused a great stir. So it's good to know what it is, how it works, and like how good it is compared to like current models that we've used before. So just another thing that's very important is like the API pricing for like high compute use is 20 to 40 times cheaper than OpenAI for like a reasoning model O1 or GPT-4o. Also, you can download the weights for free using this thing called Ollama. So I think people use like the 7 billion distilled versions of the reasoning model and download it onto their computer. So I have some interesting results from that reasoning model. And they have a free chat feature, although last I checked, you couldn't make a new account because I guess they have so much traffic. So that's kind of interesting. So I guess first things first, what is DeepSeek V3 and DeepSeek R1? So it's a very large, sparse, highly parallelized large language model. So there's no image component, it's just a large language model. And just like many large language model kind of setups, there's some pre-training, some fine-tuning, and then some reinforcement learning for alignment/reasoning. There's also a reasoning model called DeepSeek R1, which is fine-tuned. And this one has large-scale reinforcement learning for reasoning, as well as some supervised fine-tuning. So we're going to be going into both of the details on both of those models. So just as an overview, first, I'll do a taste of some architecture deep dive. So some of the new stuff from DeepSeek, or just in general, some of the new architecture things that maybe people don't know about, like multi-head latent attention, mixture of experts, and multi-token prediction. Also, I'll go over pre-training, so the model size, the dataset details that I know, which is very little, the learning rate setup, and some performance details. And finally, I'll go over post-training. So how does the reasoning model work? How is the RL trained? What's impressive about it? How is the chat model trained? And so also, during the architecture part, I'll try to highlight when something is new, like first introduced in the DeepSeek V3 paper. Because I think that's also interesting. Like, what do they have before, versus what is new? Because there are DeepSeek V2 and V1, which have a lot of these things, which didn't cause, I guess, NVIDIA to lose $500 billion. So maybe it's interesting. And of course, feel free to ask questions at any point.
Sorry, can you say that last one again?
There's a DeepSeek V2 and a DeepSeek V1. The V3, which is the current one. But for instance, multi-head latent attention was introduced in DeepSeek V2. And mixture of experts has been in many models that are not just DeepSeek. For instance.
You'll point out
what the new things are. Yeah. Sure. And then some of my final thoughts. So I guess first, this is kind of a vision audience and other people. So I'm not sure how familiar everyone is with some of like the standard-ish large language model things. So first I wanted to go over KV caching. Specifically, we're going to go over like two-headed attention. Okay, so we have some input features. First thing we do is we use our matrices to get ourselves our queries, our keys, and our values, right? We do queries.keys to get some attention maps, right? We do a weighted sum of our values, and so on, right? One thing you notice is for our next token, our next queries need to attend on the keys that we just generated, right? Our next token is going to attend on all previous tokens. So we actually need to keep those Ks around for the next token prediction. and the values too, because we're going to do a weighted sum of all the previous values for our next token. So what do? We cache the keys and values, we persist them so that we can use them for our next token prediction. Okay, we compute our token, right? For the next feature, right, we're dotting our queries with our current keys and our keys from the previous tokens, right? And so now that we have those cached keys from the previous tokens, we don't have to recompute them, right? That's the advantage of the cache. We kind of save all of our previous keys, so we never have to recompute them. Right? Like before, we do our softmax, and then we cache our keys and values from this step, right? And finally, I'll go through it one more time, right? We calculate our queries, keys, and values. We attend our current queries on all the previous keys, do a weighted sum of all the previous values, and then create our last token, okay? So that's just kind of standard KV caching, right? We're kind of storing all of our previous keys and values so we don't have to recompute them, okay? Every time. One thing you might notice is like the size of the KV cache, it's linear in terms of the size of the keys and values, right? So if I have n tokens that I'm attending on, right, then I have like O of n keys that I'm storing, right, and values that I'm storing, right? So you can imagine this is very expensive from a memory perspective, okay? So one solution that people use is grouped query attention. So in order to simulate as if you're doing two-headed attention, you only have one set of keys and values, but you have like two queries per set of keys and values. So the idea is here, you're kind of acting as if you have two-headed attention, but you really only have one set of keys and values that you're storing in your cache. So that's like kind of cheaper, right? But the DeepSeek researchers found that this like slightly degrades performance. So instead, they have this idea of multi-head latent attention. Okay, so it's pretty simple. You create your queries, and you also create some small latent vector. Okay, and then the idea is with this latent vector, you cache that small latent vector, right? This is smaller, so you can cache more of them. And then you use up projection matrices to turn that single cached small latent vector into keys and values. Okay, and then you go ahead and do your attention, right? You go to your next layer. You create your small latent vector again, cache that, output your big keys and values from that small latent, right? We're only caching the small latent, and then do your attention, okay? So they found that this kind of works better, right? You have less of a memory footprint now because you're caching this small thing. Yep.
Where is this small thing coming from though? Like you see that you generate, is it just that you backpop into this?
No, so in the same way, like where do the keys come from? It's just a learnable matrix from the input features. So this,
In this case, how? Is there a projection matrix that makes it smaller?
yeah. So you have like maybe input features of size 500. You project down into a small thing of size 10.
Okay, so your QK essentially is now not the size of the transformer embedding dimension, but the latent dimension.
Yeah, the latent dimension.
Okay.
Is it trained together or do you?
Yeah, it's chained. Everything's trained together.
I guess this is always true for all values and keys are usually some sort of linear function of some embedding anyway.
Yeah, exactly.
You could have just stored that embedding instead of key values.
Yeah, exactly. So you can think of it as like you're kind of saving space. You're doing some embedding, right? So to me, it also kind of has connections to low rank adapters in some sense. If you expect that your attention, like your optimal attention is stored in some low rank space, then this is equivalent to just making that explicit, right? So it's that's the way I think about it. And so actually,
Kind of the PCA, right? And just store the PCA components.
yeah, that's another way of thinking about it.
You know, so in order to
They're pretty spread out.
value the
Yeah,
key.
I don't think Trini likes to rely on.
It's a linear.
It's
a- Yeah. So everything's linear. Linear
We
dot
don't have any support in CSP.
Like it's not really each programming, well, I've been most here.
Can someone
Greece has done some,
who's on Zoom? Oh,
Nina has done some with me for advising.
I don't know where this. I'm not.
So that's, and maybe others, but I mean.
Okay, well, I can just turn it off for now. But anyway, continue.
Sorry, so when I normally have a transformer, if
Yeah.
I am trying to predict the fifth word, the first four word embeddings all listen to each other, right? And like so the embedding of the third word also is listening to the fourth word embedding when I'm training at least.
Well, I guess you have your like attention mask. So the third is listening to the second and first. Yeah, you have your causal mask.
But
Yeah.
And even if I'm predicting the fifth word, given I've seen all four words before,
Uh-huh.
that point.
Like,
And then the embedding that's computed for the third word
Yeah.
only sees words.
I
after
see.
the
yeah,
third
and
word.
so when I'm on the fifth word and I'm looking at the fourth word still can only see 3, 2, and 1. So I can use the from last. Yeah, yeah. And so something that's interesting is you can think about this, right? What am I doing? I'm up projecting a latent vector into a big key and then dotting. It's actually mathematically equivalent to down projecting my query and then dotting. So you can actually not have to go into this expensive space and do dot products. You can actually do dot products in this kind of cheaper space, which is kind of nice. So you both save memory and you also save like throughput. And so at this point, you might be thinking, well, you're just doing smaller attention. Like, what's going on? And so, yeah, so the way I think about this is, right, we're kind of thinking about Pareto frontiers, right? So if I have a compute budget, I'd rather have more smaller attention than have less larger attention. Right? So if I have some fixed compute, I can do more layers of small attention than I can do like less layers of big attention. So basically what they're saying is like the attention operation, doing that lots of times, like this very deep network is very valuable. It's better than doing attention in these big blocks.
Okay, but then by that logic, why not just reduce the transformer embedding dimension and just do the same thing that you normally do instead of this like weird.
I
It's
guess,
almost the same thing, but you're just like up projecting it back to the original dimension.
yeah, but you also save space because your keys and your values are now stored in like one vector.
Or maybe it's that like you want the attention to be in the lower dimensional space, but you
Yeah.
want like the MLP part of the transformer still to be in the higher
Yeah.
dimensional space.
Yeah, yeah,
And like you want that like
yeah.
the information to be held in these like.
Yeah, so your output space is bigger. Also, I think it is non-trivial that like you're storing one latent per both key and value at this point.
Yeah, it
Right.
seems like another perspective on this is that, okay, you have small queries and small keys, but now instead of separately storing a value,
Yeah.
you can take your key and do a linear transform and get the value from
Yeah,
that.
exactly. That's another way of thinking about it. So I guess this is one thing. So this is for the attention block, right? And so we know transformers, there's an attention, and then there's some MLP after, right? And so for the MLP, this mixture of experts idea is brought up. And so this is from a DeepSeek mixture of experts paper from a while back. This is not from DeepSeek V3, this figure. But the idea is it has 16 billion parameters, as you can see up here, but only 2 point something are activated per token, right? So what I think about this is you want scalable parameters, right? Scaling laws say if you have more parameters and more data, it's better. However, you want low computational costs per token, right? So that you can kind of meet your hardware constraints, right? So I don't want to have that many activated parameters per token, but I want to have like a lot of parameters in my model. And I also want to use all my parameters kind of uniformly, right? Like if I have a bunch of parameters, but I only use an eighth of them, that's just a model that's an eighth as big, right? So I kind of want to use all my parameters uniformly and sparsely, right? So if we look at this basic transformer block, we have this transformer block and this feed-forward network. Mixture of experts is kind of like you have your transformer block, you have many small feed-forward blocks, but you only activate some sparse number of them per token, okay? And so we can go over how mixture of experts work, okay? So first, you can imagine I have these 5 randomly initialized mixture of experts models, and I have these 5 orange randomly initialized features that are the same size as my input features that are coming into the model, okay? So first thing I do, I dot my input features with all of these learnable, like they're called centroid features in the paper, okay? So I get maybe 0.1, 0.5. I smooth them with a sigma also, so they're between 0 and 1. From there, I pick the top K of them. Okay, so in this example, it's 0.8 and 0.6. Okay, those are the top K. I only do computation through those sparse set of experts. And then I add the results and I weigh them by whatever my sigmoid said. So I'm doing 0.8 times expert 4 plus 0.6 times expert 5. Okay. And so one thing to note is you're going to backprop through the experts and the centroids. So you're backpropping through everything. And like for, I guess, nerds, it's not an exact like differentiable function because you kind of have like some like some sharpness going on, but like it's fine. And there's many things done to try to make the routing good. And by making the routing good, I mean you want to kind of route uniformly. So you're kind of taking advantage of all the experts, right? No expert never gets used. No expert gets used too much. Okay.
And this
Okay.
always happens at the MLP.
This is the MLP, yeah. So we saw how to make the transformer better. Also, transformers are like, by definition, kind of parallelizable by the different.
Wait, each of these experts are just like MLP.
They're smaller MLPs, yeah.
Okay, okay.
Yep.
You just don't use the other one.
Yeah, you don't use them, yeah.
Did they like manually say we want X different experts and this is what each expert is gonna do? Or
No,
is
it's learned. Yeah. Yeah.
Does it matter how much the experts come to like depend on each other? Like if you want each of them to be an expert in its own domain, kind of?
There is a notion of having, you don't want two experts to learn the same thing. And so I'll talk about how they avoided this. Yeah, and yeah. No question, okay. So I guess let's look at some DeepSeek mixture of experts improvements. They have more smaller experts. That's one thing they found is better. Highly parallelizable, and they found that like, this works better. So maybe my analogy is like a conv next block, if any people are familiar with that. It's like more smaller parallelized blocks. Also, to address this problem of like, you don't want two experts to learn the same redundant information, you have some shared experts that basically are always on, right? And so what you're hoping is that those kind of absorb information that you kind of always need, so that your other experts are kind of uniform. So you never explicitly say don't learn the same information, but you say, hey, I'll have a few that always are on. Okay. So that's another thing that people do, that they did. And so this is from DeepSeek V2, I think, or maybe it has its own paper. Maybe it's in the mixture of extra paper. What is new is that they have a new way of load balancing. And so load balancing basically means, how can I force all my experts to be used uniformly? And so the idea is, say expert 4 always gets used, right? Its sigmoid with the vector is always very high. You just say, oh, that's bad. Let me just downweight that dot product value, and then it'll be used less. No, they just downweight it. It used to be a loss, and then they said it's just better just to downweight it. Only during training. I mean, not manually, but like, you can you run some statistics every so often on how much the experts are being used. And if it's being used too much, you downweight it. But notably, this is only downweighted like when you're choosing. So if you still choose expert 4 in this case, you'd say, okay, 0.9. It's okay, it's fine. So it's just to get it used less. Yeah. It's after. So it's like the equation is like dot product minus some gamma, which is decided by your statistics. Yeah.
Did they downweight it such that all of them are going to be used equally?
Yeah,
or
yeah. So if
do they have some tolerance?
it's just if you want them all to be used equally, so if any one is being used too much, then you downweight it.
At this point to use the shared knowledge and redundancy?
Basically the idea is that if I have some experts that are always used, the hope is that those kind of learn information that you always need, so that the other ones don't have to share learning that information. Register tokens, not sure, but I guess that was the intuition that was provided in the paper. It's like, hey, if I don't have these, then they all kind of learn the information that you always need. But if I have these, those kind of learn something that then. And so I guess one last thing I'll say that I didn't mention in the slides is that they also have a fixed number of experts, or they have a fixed number of nodes that you can use. So say like you have a GPU cluster of like, you have a node of 8 GPUs. Say I have 6 of those, and each node contains 2 experts. Maybe you can only use 2 nodes, right? So I can use 4 experts and 2 nodes, but I couldn't use 4 experts, 1 from each node. And the idea is that like that would add communication overhead. So ideally you don't want to do that, right? And they also do stuff like if you have an expert that's still being used a lot of inference time, you just make 2 of those to make the communications a little bit better. So you add some redundancy there as well. So it's not perfect. So yep, this downweighting thing is new, by the way, not having it be a loss. That was new to V3.
I thought here experts is like primary care providers, so they and they have their own issues.
Yeah. Yeah, so that's also good.
Kind of like what?
Like a primary care provider. It was like handles everything. And then you need a specialist, like it's time to go. So I guess they always also do this multi-token prediction thing. So you can imagine attention is very costly. So if I can predict 2 tokens at a time, I'm like going almost twice. I'm going like 1.8 times as fast or something. So the question is, how do you do multi-token prediction? Pretty simple. You have your input tokens. You do attention on all the previous tokens. You get your output token, right? You take your features from that total all attention thing and your output token that you just generated, and you use just those 2 things to generate the next token. Right, so in the second block, I'm not doing attention with everything that was before me. I just taken my features from my previous thing that did take in everything before me and the token I predicted, and I'm generating a new token. And also notably, this second model has a bunch of shared weights with the first model. So if you're familiar, like they share like the final like, output head, they share the input, whatever layer to try to save parameters. And also it's sequential, which I think is new. I think previous work that did multi-token prediction just parallelly generated multiple tokens in a row. And so they found that sequential works better. So I think in the final model, during inference, they do 2 tokens in a row. But I think during training, they do up to 3 or 4 tokens predicted in this manner. Yeah, because you're not doing attention with the whatever 128,000 tokens from before. That's the big thing, is the context like so big. Okay. So I think my takeaways on architecture are the following. Like, I think there's an analogy of like, if you want to be the best at doing something, you should try to improve by 1% every single part of that thing. Right. So if you want to be the best at like running, if you want to be an Olympic runner, you need to make sure you have the best shoes, have the best conditioning, also get the best sleep. Right. And so to me, like the architecture is very clear that like for every part of the training process and architecture design, a lot of thought was gone into how to make it. A lot of ablation studies were performed. Everything's very succinct. So I thought that was really cool. And I'm not even mentioning things like they have a bunch of stuff for how to do mixed precision. So I think previous models, like large models, aren't trained with mixed precision. At least Llama 3 point whatever was not trained with mixed precision. So they talk about how to train with FP8. As you go from FP8 to like BF16 to float 32, and then you go back, and there's a lot of work there. Then there's a lot of work in how to communicate the forward pass and the backward pass and how to overlap. And there's a lot of stuff like that as well. So there's clearly a lot of attention to detail in all these things, which took a team a long time to figure out and implement and ablate. I think that's something that I definitely want to emphasize. So I think like a lot of like one thing I've seen a lot is like, oh, $5 million for the final training run is so little. But like to be able to develop all these things and test them and show that they work and get the implementation level details definitely took so long of very smart people working very diligent on every single part of the process. Like from like hardware, or not hardware, but from like the actual communication to the nodes, to getting things shut down, to the architecture, etc. And to the data set, etc. Even though the data set isn't public, I'm sure that also there's a bunch of people working on how to clean the data, how to input things in the right order, etc. They released the model weights, but none of the training data.
But these designs and so on, they are.
Yeah, I mean, and you have the weights and like the ability to run them, so you can like look.
Okay.
Yeah. Yeah.
I think they have like 4 IOI gold medalists.
Yeah, so like also like one thing is like, yeah, like for each one of those dudes, like the cost of like paying someone like that in the US so high. Like you have to like basically be equivalent to like a quant firm, so high. So I think that's also like something that's important to note is like it's not like, oh, you give someone $5 million, they could do it. It's not like definitely orders of
Yeah,
magnitude.
but I feel like maybe more quant company in US is just start training these models.
Yeah, like Jane Street, yeah. Okay, so this is good. We're at 30 minutes. We can talk about 30 minutes of training details and R1 stuff. So first of all, number of tokens for pre-training is 14.8 trillion. That is all we know. My knowledge is that's in line with other similar size model training. The tokens.
That's a silly question.
Yeah.
So, much of the fanfare was that this was only, was it $1 million to train?
5 million, yeah.
5 million? So I'm totally miscalibrating. So what is the normal cost to train?
So I guess it's hard to say. So this slide will have some of that. Yeah. So first of all, there's 671 billion parameters. So that's more than like the whatever Llama 300 billion. It's like a little more than twice, but only 37 billion are activated per token, right? Whereas the Llama model is like a dense model. So you need more memory to get it done. That's another thing that's pretty interesting. But I guess I looked this up. Yeah, the experts. So this corresponds to like 400 gigabytes of model. So you cannot download the full thing locally and run it. So when people say, oh, I downloaded DeepSeek, they're talking about the 7 billion distilled model, not the 600 billion mixture of experts. Yeah, I'm not sure. I don't think so. Yeah.
So you're saying that the experts allow a much smaller memory footprint. It should also be faster.
Yeah, yes, I think so, yeah.
than
Yeah, yeah, yeah. And it's like 1.8 times faster than doing it every step. So I think Llama doesn't do sequential token prediction, like 2 at a time, if I remember correctly.
Wait, so none of these tricks are in the distilled model, these are only in the big model.
There's multiple, I think, okay, we'll talk about, there's different types of distillation. We'll talk about. Yeah, so it's still like, yeah,
So those are gonna stay idle every time we run inference, right? It's not all experts.
But I assume because of this big memory, when it must be that the experts, like that centroid is way smaller than the NLP. Because otherwise, you wouldn't get this like.
yeah, I'm not sure about, I think they all get used, so I think. Yeah, I'm not sure about the communication from bringing the experts. I don't know if they're all on a GPU together. I'm not sure. Yeah, yeah, they do LSDP for sure. Okay, but let's continue on. I think there's also some interesting things. So they do fill in middle autoregressive training. So this is like you give it the start tokens, the end tokens, and the middle tokens last. So you can think about autoregressively. That means you generating the middle tokens after knowing the start and the end. And so this is helpful for tasks like coding. Right? If you think about using Copilot, right, the model is prompted with the code before you, the code after you, and is asked to produce what you're trying to generate right now. Also, Adam W, you know, the good old fashioned Adam W. Linear, I mean, there's so many things about, oh, we have a better optimizer than Adam W I've seen. Seems like Adam W is still the big dog. A linear warm-up, cosine decay, then constant linear lower rate, and then final drop to lowest constant level linear learning rate. So to me, that seems pretty normal. Nothing too crazy there. So this is the thing. So they said it took them 2.788 million H800 GPU hours for the final training. Corresponding to $5 million in pure training cost. 2048 GPUs, 8 GPUs per node, 256 nodes. So the Llama model said they have H100s, 16K H100s over 54 days. I calculated that this was 20.8 million H100 hours, but then Lucas Bayer on Twitter said it was 30.8, so I was confused. But it's definitely at least around an order of magnitude more GPU hours. If we were to believe both people, I guess, which we do.
Roughly speaking, that should be a $50 million model.
Something, yeah. So like, it's very expensive.
Sorry, but 800 GPU was the base.
So I think I looked into this a little bit. My understanding is that 800s are like, H800s are slightly worse, but like not too much worse. And also there's like speculation about like them having H100s and like Singapore buying a bunch of H100s and then, but I won't get into too much of that. All we have to say, all I can say is that I believe the final training was with these GPUs, but in terms of ablations or anything like that, it's not reported, so who knows? And clearly, many ablations were done. I think this is a point that I really want to hammer home. Many ablations were done. Okay, let me check chat.
And then you get this opinion because of the
Yeah.
tables in the paper. Like, how do you know that there are many of
Oh, I just like, because every single thing they talk about, like how they did it specifically, and like, oh, it's worse than this version, or it's better than this version, like, or this version we see didn't work very well, so we did this instead. There's constantly things like that.
Yeah, I assume like all the big houses.
They do have a lot of, but like they cover more stuff. So like for instance, like the big guys, they didn't, or Llama doesn't have any of the mixed precision stuff, for instance. Like I don't know enough about communications. They both had some communication diagrams that look like arrows to me, so I don't know. But definitely there's more stuff in terms of like more like individual things. Okay, let's continue on. Yep, and the context length is the same as GPT-4 Turbo, so I think it seems fine. They use some paper to extend the context length, which used some fancy rope trick, which I did not understand that much, so I kind of skipped it. But you can look into the math. It's called Palm. It's an archive paper. Okay, so now let's talk about R1, DeepSeek R1, because I think this is really the model that like caused everyone to kind of go crazy. And I think this is also because OpenAI like did a good job of marketing their reasoning model as like so like fancy and like state of the art. So for instance, I don't know if you guys went to Noam's talk, but he was like, oh, I can't tell you any of the details, but it was large scale RL and it works so well, right? So they did a good job of marketing. But anyway, I think it's the actual training setup is not super complicated for DeepSeek R1. So I don't know how many people here are familiar with reinforcement learning, but if you look at group relative policy optimization, which is like basically DeepSeek's PPO or general RL training framework. First of all, there's no value function that's learned. So I think they said that like having a value function adds extra overhead, adds complexity, so it's not good. But just looking at this equation here, we have some min of some clipping some stuff and some 1 minus epsilon and some 1 plus epsilon. Looks like PPO. We have some beta times the KL divergence term, which is also like something like that people have used in RL. Looks like TRPO to me. And then finally, we have this advantage function, which is pretty common. I think usually it's like whatever reward minus like value plus gamma. I don't get it wrong. Katerina's gonna come out of me, but something like that. Anyway, the point is this reward is kind of like a reinforced type of reward. There's no value model. You're just looking at how good is your reward compared to the average reward from your batch. And you're dividing by standard deviation. Okay. And so they just use this hard reward with problems like math or coding, where you can actually verify if it's right. Right. So for math problems, there's a correct answer. For leak code style or code forces style questions, you just have some test cases. You can see if you got it right. And so the reward is just, hey, did you get it right? And did you format your answer as think, and then answer? That's it. So the actual reward is not that complicated.
Naive question.
Nope.
So normally, when you do model training in a recursive fashion, you're always optimizing for the next token you see in your actual training set. So this is, I always thought that this came into play when you have humans in the loop, or you have some special kind of, you're not just training on sequences of tokens anymore, you're training on something else.
Right. No, but they're saying, no, you just, it's easier. It's in some sense easier than like a human feedback type of thing, because you have some hard reward. Like for this human feedback thing, your reward model is estimated from human preferences. But for any problem, the question is, the answer is either 3 or it's not 3, right? You got it right or you didn't. So you can use that like ground truth reward and just say, hey, can you get to that ground truth reward? How can you get to it better? Right. So it's nothing to do with like sequence or cross entropy.
Say that like all they did was like just do RL like for coding, but then like you just start from an LLM.
Yeah. But also one thing is it's very unclear to me. They didn't say what data they used. And they didn't even say how long they trained it for. I looked very close. They just said thousands of RL steps. So it's clear to me that there's no way they didn't spend a bunch of time figuring out exactly what data works the best and how to batch it correctly and how to do all these things. Because reinforcement learning is like notoriously tricky to get right. Right. And so they just don't mention any of that.
Especially sparse.
Yeah. So I think this is one of the unseen things, which is like, oh, it's open source, but I'm sure it is not trivial to reproduce the results.
Like things where you're producing long bits of code, this almost seems like magic to me, because
Yeah,
I would
it's
guess when you start, everything is getting 0 reward because none of the code necessarily executes or
see that.
I suspect it's
I don't
some
know.
curriculum-based
Yeah, there might be
things.
curriculum.
So these models are decent at coding for like
Yeah.
easier stuff, right?
Yeah.
You start from there, then you do these sparser word stuff, and you kind of keep doing it.
And maybe that kind of thing is exactly why they didn't talk about it. And they just say thousands of RL steps, lots of data.
That doesn't sound like a lot of steps. to be honest.
Yeah, so but
Usually million, billion scale.
but I don't know.
By default.
That was saying that the base model is the secret sauce, because people have been trying this from 2 years ago.
Interesting.
Base models are just too bad at coding to get
Interesting.
convincing.
And actually so I think this is a good point that he brings up about like if the base model is good, then the RL will work much better. Because they did some ablations later where they said that like if you try to do this RL with like Quen 7 billion, it basically works it does not work. But if you distill the good RL chains of thought from R1 into Quen, then it does work much better. So I could believe that if you have a very strong base model, it significantly helps unlock in some sense.
That the whole O1 thinking and test pending is bullshit. And you're just like,
Well, I mean, if it works, it works. I mean, but like the idea that it's so mystical maybe is a little bit smoke and mirror. I'd see that, like the idea that's like, oh, it's so fancy.
There's no test out. Chain of thought thing, right? Like it's just directly getting the answer.
Actually, so this is a good point. So we talked about like one thing that people have been trying for a long time is just like, oh, let's give it a reward step by step. So they actually said they tried that, and it's tricky to figure out how to not get the model to reward hack, which is if you have some neural reward, it just learns how to get that reward really well, even without solving the question. And they also said they tried to do some tree search, but it was hard to do it because you're kind of tree searching over this kind of token space, which is like very tree theoretically big. And so one thing that I thought was interesting is this graph on the right here is the number of tokens it's using to think per step. And so if you notice, like the number of tokens it's using to think is like increasing, right? So it's kind of thinking for longer and longer as it is getting higher and higher rewards on a benchmark like Amy, right? And so that's something that I thought was interesting. So I guess the DeepSeek R1 setup is basically, they realize that if you just do pure RL, since there's no like reward for anything other than getting the right answer, it'll do stuff like switch between English and Chinese. So it's trained on both models. And it'll do stuff like ramble a bunch when maybe it doesn't need to, right? And it does stuff that you wouldn't want like a model that you release to people to do, right? And so they said, hey, how can we take this idea and turn it into kind of a palatable model? And so first, they fine-tune with some carefully curated reasoning data, right? And so they're just doing fine-tuning on some trajectories here. And so I imagine this is maybe part of their data set that they were using for training, that they actually like developed, like they had prompted the model with chain of thought, maybe picked the ones that looked the best, etc. And so I think I wanted to highlight this quote, which is from the R1 paper, which is, by carefully designing the pattern for cold start data with human priors, which is like, you know, we pick which chain of thoughts go in there, we observe better performance against DeepSeek R10. We believe that iterative training of doing both supervised fine-tuning and RL in iteration is a better way for reasoning models. And they kind of don't touch on this again, but it seemed to me to be pretty important. The idea that kind of you want to do RL to kind of have the model learn how to reason itself, but you can kind of supervise fine-tune with some data about your reasoning should look kind of like this. And it can still work basically to the same effect while having much more palatable reasoning.
Wait, so just to clarify here, what is the action space of the RL part? Is it like predicting chains of thought?
It's predicting
So
like,
the model is fixed, the base model. And then it is just predicting the chains of thought.
and then it's like updated like via gradients. But yeah, it's predicting like a think token plus chain of thought plus end think token plus answer token plus answer plus end answer token.
And let's pass back into the model.
That's like sequentially you're saying?
Yeah.
I guess sequentially the first think token is passed in and then it's just sequential generation. So yeah, it's still like an autoregressive. Yeah.
That's what they say in the abstract, where they say, oh, without SFT, everything is.
Yeah,
fine.
so it's a little bit weird. Yeah.
What happened with the R1 starting model, right?
Yeah.
Now it's that one, right?
Yeah, so I do agree. It's a little bizarre that they mentioned it. But yeah, so I guess they fine-tune with this cold start data. Then they do this large scale RL as before. They say they add a tiny reward that says, don't language switch. Which they said like basically made it not language switch and like only slightly degraded performance. So that's good. Then they say once converged, you collect more data. You kind of do your rejection sampling. So you collect a lot of data from R1. You maybe have DeepSeek itself figure out which ones are good, which are bad based on your own prompting. Like, hey, make sure it doesn't ramble. Make sure it's at least a little bit concise, etc. You also get some good non-reasoning trajectories, like some writing, question answering, etc. You prompt the model to do a chain of thought. You pick the chain of thoughts that look good, right? You do some more rejection sampling. And then you supervise fine-tune on that final data set of like 600K reasoning, 200K non-reasoning. Okay.
Sorry, when you use the term trajectory, should I think about that as a sequence?
I think you can think about that as like think token, think, end think token, token, answer, and answer token. That's it, yeah. And so you do final SFT on this data set, which is like your kind of cleaned 600K reasoning data that you generated from your model and your cleaned 200K non-reasoning data. Once you do fine-tuning with that data, then you finally do some RLHF. So they don't call it RLHF. They say we do reinforcement learning with our own internal human-based reward models. I mean, call it what you want, right? And then they say they do some more GRPO. And so I just wanted to also look at some of the results. Specifically, the Amy benchmark does pretty good, 79.8 compared to 01, 79.2. So basically it's doing just about as well. Code Forces, this is another like coding competition type thing. 96.3 versus 96.6. So it's basically doing just as well. And then this SWE verified benchmark where they're both doing under 50%. So just to give everyone a concept of what the SWE verified benchmark is, basically you have a large code base, you have some pull requests saying, you know, you intern, fix this thing, right? And then the model needs to go in, make changes to the code base, And then it's tested on unit tests, both, hey, did you fix the thing that your boss told you to fix? And did you not break anything else? Right? And so I guess the point is, once this gets to like 95%, like no more free lunches at Meta for us. I guess we're good, we're AI people, but I think people really care a lot about this verified benchmark and other types of benchmarks for like having someone who can just manage a bunch of AI systems and write code that way. So I thought that was interesting. On some tasks, I guess for Sui verified, yes. I guess they get clapped on the Amy, but yeah, I think the point is most people agree that this model is much better than O1 mini at 4.0 for reasoning. I have seen debates on both sides about if it's better than O1 or not. But surely if you look at the Pareto frontier of cost per token, it's whatever, an order of magnitude better, because it's at worst 98% as good. Right. And so this is the big thing from an investor perspective, right? They don't care, like as a consumer, right? Like a normal consumer, you don't care about that extra 0.3 on Sui verified. You just say, hey, I want to pick a cheaper model. Yeah.
Yeah, discussion, but how fast is inference compared to O1, etc.?
I don't know. I mean, I tested a distilled version. I guess it's as fast as they can generate whatever the 10K tokens. So it's just however fast the original model was for that many tokens. So I don't know. I think they claimed that this model was like faster because they're doing sparseness, but I can't tell you if you add in all the tokens, and I don't know how many tokens O1 uses because it's closed off. So
The cost comparisons, we don't know.
like for inference, I don't know. I'm saying. Yeah, but I don't know how many tokens O1 is using for reasoning. And I don't know if they have some in-house stuff where they said, oh, it takes 10K tokens. Can we make it less? I have no idea. So I feel like I'm not in a position to comment on something. Like the size of the reasoning. Sorry. Because if this takes 10K steps to reason, and in OpenAI, it took 10K steps originally, and they were like, this is taking too long. Can we distill it to 2K steps? Right? I haven't used O1 enough to really have an opinion on this.
Dumb question, for code generation, when you say you do it in fewer tokens, does it mean the code is smaller?
I guess the code that they generate is like the answer part. So the reasoning part is still long. Yeah. So I guess also I was a math major and I like combinatorics a lot. So I thought I'd give it this combinatorics question that I thought was pretty hard at the time. So basically the answer is 1. So I only gave it this right-hand side, which is like this like weird combinatorial sum. Which just happened to come up in like a random side project. So it's not like, I know it's not on the internet because I could not find it when I was trying to solve it. And it ends up being 1, but like the way in which R1 solved the question was pretty interesting. And so also just as a disclaimer, this is not R1 671 billion. This is a distilled R1 that like can be downloaded on the computer. So even it's less strong. So if it solves it well, it's more impressive. But first, I thought it was funny during its initial thought, it said, let me recall. What are you recalling? Your language model? Secondly, it changes some math around. It says it aligns with the identity I was thinking of, which is correct. It had to do some re-indexing to get to the correct hockey stick identity, which is a combinatorial identity with choosing functions. What was most interesting to me was it kept going back on what it said. So it got that the answer was 1, and it said, wait, that's surprising. Let me verify step by step. And then it did it again, and it said, wait, so that's it? The entire expression simplifies down to 1? Is this correct? It seems too simple. And then it said, wait, let me try plugging in small numbers. Let's pick n equals 2, k equals 1, etc. And then after that, it said, yes, it is 1, answer 1. Yeah. So my opinion about the extended context length, and it just learns to just keep trying. It says, hey, if you, it's useful, right? If you give me 10K tokens, I might as well try it a bunch of times and like really make sure I'm correct.
Conversation.
No. It just said think, answer 1. So it's actually pretty cool that this kind of thing can be unlocked with like RL. That's kind of sick in some sense. I was like, wow.
So like,
So
what's
then,
the inference cost? So you ran this on your laptop?
I ran this on one of my friend's laptops. So it took,
So
I
it
guess,
doesn't need a
no, because Llama, I guess they have some custom something that lets it run. So it took like, I don't know, 45 seconds, a minute.
Do you know the GPU that cost for running this approximately?
It's a distilled Quen 7 billion model. So however much Quen 7 billion costs. I think 20 gigs, 20 something gigs. Yeah, but that's the distilled version. So that's not the version that will get whatever 90% of Amy.
I did, and I see the same thing.
Yeah. So I think, but I think that's almost like it learns that that's the way to really make sure you know. So I thought that was really interesting. So I guess now we can talk about DeepSeek V3 post-training. I think the numbers are not important that much, but like a lot of them are bold, which is I guess is good. My opinion is that like it definitely does much better than all the open source models, and it seems to do better than 4.0, and people seem to think consistently. I have not seen anyone that said, oh, GPT 4.0 does better than DeepSeek V3. I've never seen that. Whereas I've seen both sides for kind of 0.1. But yeah, so I guess it's kind of similar. They do supervised fine tuning with some R1 trajectories, some DeepSeek 2.5 chat trajectories. And they do some like RLHF type stuff. They do some LLM as judge type stuff. So they'll maybe generate 10 creative writing outputs, then ask the model which one it likes the best. And so they actually explicitly mention that they think this is a very promising direction, probably for the same reason, which is as the model gets better, it's a better judge for itself. Right. So I thought that was pretty interesting as well. And so that's just DeepSeek V3. I thought I'd do something about, I have a slide on distillation. So like I kind of mentioned before, they said that distilling R1 reasoning data into smaller Quen models significantly outperformed just doing RL on Quen itself. So this kind of leads to the idea that having the strong model is super valuable for distillation. Right, so if you just look at this Amy, this first column here, this QWQ model is like 50%. If you do this R1 training on it, it goes down a little bit. But if you distill with the good trajectories, I guess it learns to say wait a bunch of times. It goes up significantly. So I thought that was interesting. So it kind of leads to the idea of having a powerful model distill a smaller model is very good. And it's very useful.
That world went from 50 to 47.
That's what they're saying, yeah. And it improved on, I think, all the other ones, or almost all the other ones. But like the point is, it no way performs similarly to the DeepSeek model RL. Yeah, it didn't really help us much. So I think this also goes back to maybe why people couldn't get RL to work before on other models. They didn't have enough capacity in some sense. So I guess the final thing I'm going to talk about is unknowns. So like we said before, what data was used to train these models? Surely it was bootstrapped from Claude and GPT, etc. If only because they just showed that distilling is super effective. So why not distill? And also, like, if OpenAI can scrape the internet, they can't really be mad at people scraping them. How clean prepared was the data? My opinion is that large-scale effort was gone into cleaning the data. Maybe, like you said, doing some curriculum learning for RL, but all of that is kind of behind a black box. So it's not really open source in the sense that anyone can reproduce the results, right? How many GPUs did it have for research and development? After reading the paper, lots of ablations would have to be performed over many papers to get to this level of performance. So doing all of that, it's unclear how much it was. I think one thing that spooked the market was like the pricing model, right? It doesn't make sense for ChatGPT to charge more and more money if it's reproducible by open source models that people can download or use otherwise, right? So for instance, like other apps won't do a bunch of API calls to OpenAI, which they're going to lose a bunch of money. So I think that's why the market freaked out more than, oh, this model is so much better. Like, oh, like they did it with such a cheap budget. It's more about being able to control the money of AI, which it seems is unclear how to do. Even if everyone uses it, it's unclear how to have one company that does it. And then US has like, what, 7 big companies. So maybe it's tricky for the stock market. Also, another question is, how long can DeepSeek even host traffic to these large models? I think there was a tweet from Sam Altman that said their O1 was losing money. So if everyone transitions to DeepSeek, it's unclear to me how much money it would take to even maintain that for a large model, right? And also another question is, how much do people really care about like the 600 billion model versus the pretty good distilled 7 billion model, right? It's unclear. So yeah, I think that was a talk. Thanks very much. I guess we have 5 minutes for questions.
In the beginning, when smaller models were trying to imitate proprietary models, there were these papers saying, oh yeah, you're going to overfit on this and you're going to forget other things.
Yeah.
Now we're imitating not the final answer, but the reasoning chains. And it seems this is a great idea.
Yeah.
Something changed beyond like the fact that we don't imitate the final answer, but the reasoning and the final answer.
I think that probably is part of it. But I think also another thing that like I think I've seen, which I was thinking about, is like when training the model, DeepSeek had access, like they knew what benchmarks they were going to be tested on. So in their data, they can make sure they hit all the different Amy type questions. They can make sure they hit all the different code forces type questions, even if they don't use the data set specifically. So maybe this is another reason why in their results, distilling Quen and then showing results on Amy does super well. Right, so
I didn't quite understand your comment because in my head, the words that the model produces are all its outputs and final answer, right? Like for CNNs, whatever, like if it's segmentation CNN, whatever pixel-wise output it's producing is its output. Here, all the words that it produced is the output, right? And when distilling, you're saying, hey, produce all these words.
Right, so I remember the first papers that came out, for example, do you remember this is the caveat of imitating proprietary LLMs? That was the first thing that people did. They took expensive models, they didn't know how to train them, so they say, we're just gonna imitate them. And then people were trying to make the point that if you just imitate them, then you lose all the generalization of those models because you're overfitting.
that's a good point, yeah.
Question answer pairs that you trained on. Here, back then there was no such chain of thought thing. You just imitate immediately the answer. You don't imitate the thinking process. And I'm saying, is there something really different between imitating, copy pasting? It's called spoon feeding.
Right.
The final answer versus if I give you the thinking process. Maybe if you imitate the thinking process, then it's much better than. Yeah.
I'm just confused on the terminology thinking process because aren't these words that it's actually outputting?
It's true. Also,
But
yeah.
this is a stepping stone. So maybe this, if I imitate the stepping stone of the whole solution is much, then I'm not gonna memorize it.
Sure.
I'm not gonna memorize the answer because maybe it became easier for me to actually regenerate it, something like this.
I also
I'm
don't
actually
know.
asking the question.
I also don't know, like, because they're distilling it for kind of these very structured questions, like an Amy question or so I don't know how well distillation works for like just a chat feature. Maybe that's more unclear. Because this distillation is for like, can you get the question, can you get the answer right to a code forces question? Can you get the answer right to an Amy question, which seems much more structured than, hey, can you be very conversational and like pretty nice? Like maybe that's a harder task. I'm not sure. Any other questions?
So I guess this is riffing off what we just discussed, like, so when we say chain of thought, it's really just a bunch of words. And in some sense, you were showing the chain of thought in your interaction. They kept saying, wait a second, let me verify those correct.
Yeah.
And so the claim is that now you can get those sort of chain of thought answers from a really big model. So those are much richer to train on.
Sure.
Than the actual raw answer itself.
Yeah. And I guess like, yeah, I wonder how much like the chain of thought is like it's not trained with like a reconstruction loss, right? The chain of thoughts. So another question is like, maybe the chain of thoughts are like good chain of thoughts for AIs. Like who knows? Like sometimes I think about like the analogy of like, you see a bird flapping its wings and you try to make a plane, right? Like what parts of the plane are from the bird and what parts are like, you need to make it metal, right? So the question is like, if you're trying to make an AI reasoning model, what parts of it follow our intuitions and then what parts of it don't? And RL seems like a much more like, I'm learning how I can do well type of thing than like, I'm learning what a human wants me to think. But also, obviously, this is just speculation. But that could also be another reason why it does better is kind of like the words are in a order that like the AI likes in some sense. Yeah.
Output format was like think, and then like
Yeah.
answer. Is that just for the reasoning class, like the structured ones, or is that for other ones too? Because you mentioned something about like judging people's written.
I think so. I think they do it for everything. So they also do it for tasks like question answering and like creative writing and stuff. So I think they just format it the same. But it's also kind of I think the formatting is the same across all those tasks. But you don't have the hard rewards anymore. You have like some LLM as judge rewards. I think there and there.
Do you have any intuition on why having these thinking tokens and having it, check its work over and over again works better than just querying the LLM 10 times with the same question?
Yeah, I don't know. I guess that's a good question. Maybe it has to do with reinforcement learning somehow. I'm not sure. I guess you're trying to train it specifically to get the right answer, but it can think longer. I'm actually not sure. That's a good question.
It's a chain of thought, right? Like without prompting a model to write out its steps. Like if you do prompt the model to write out its steps, it performs better. That's like it's just
that's true. Yeah. So maybe it's just an extension and then specifically trained to do better also. Yeah. I think you had a question, and then we can do you as a last question, and then
Does the model demonstrate this practice of like rethinking over its answer for questions that aren't based on math?
I don't. I haven't tried it. They does. Okay, that's funny. It could be. Yeah, I also like, you can ask it like do not hallucinate. I've heard this also. Yeah, last question and then I'll.
Do you think there's any, like, do you think there's, like, you can do something like, chain of thought in continuous space or like latent space as opposed to like explicit tokens?
Mm,
And do you think like that can improve this or like any thought on?
I don't know. It seems hard because like, it seems like going back to the point about like the good base model is really what's key. Like that, the having a really good base model seems more important than any specific implementation detail. Like that's one of my big takeaways also. Like the actual RL kind of setup didn't seem super complex, at least what we were shown. So maybe the real key is just having a really good base model. So then what you'd have to do is have a really good continuous base model, which seems hard when you have all this research and development on like autoregressive token-based models. Okay, yeah, a Zoom question. Are the centres learned? It doesn't seem very differentiable. My knowledge is that they are learned, but I think for details, maybe check the paper. I don't remember exactly, but they definitely, there are gradients going on there. Yeah. So sorry. That's the best I got. All right. Thanks everyone. Yeah.